Okay, to pick up where we left off, we finished that first example of an inelastic collision, and now to continue with the class practice, we will look at the second inelastic collision example. The blue and green train car are back, but this time you'll notice that due to the wording, they're now stuck together, which would imply, as you're encountering these problems, words like that would imply that this is definitely an inelastic collision, so that you can pick the right formula and then apply it. So the blue train car and the green train car collide inelastically, and we want to know what's the velocity of the stuck together train cars after the collision. So if you can flip to the front page of the collisions notes, you'll find that the equation that we had from the previous slide is still there. Initial momentum of object 1 plus initial momentum of object 2 is equal to the final momentum of the stuck together unit. Let's plug in the numbers. Blue car we'll call object 1, so here is its mass and velocity, 1 kilo, moving at 2 meters per second initially. The green car, in the beginning, it has a mass of 1 and it is stationary, so we can plug in that velocity 0. Now they're going to collide. So the end scenario, we need to add together both masses, 1 and 1, and we can solve for the final velocity of those two moving together. For the conceptual thinkers, you're probably guessing that, hey, if this object by itself is moving at 2 in the beginning, but now in the end, I have a unit that's twice as big, what kind of velocity is it going to move away with? Let's find out mathematically for those that don't already get the concept. 1 times 2 gives you 2. The 1 times 0 is gone, so the left-hand side only remains as 2. On the right-hand side, we add together the 2, and here it is multiplied by VF. We just copied and brought that on down. When you divide it, you find out that the final velocity of the stuck-together unit that's twice as massive is 1 meter per second. Again, twice as big, half as fast. That's the big concept here. If the concept escapes you, then of course you can approach this mathematically and you'll still get the answer. Last type of collision, let's flip over to the title page of the collisions notes and let's fill in what recoil and push-off collisions are all about, also known as action-reaction. You should fill in that for recoil scenarios, the total momentum of the entire system is 0. It cancels out. But that still means that, yes, everything is conserved because we have the interaction of the two objects being equal. There's your hint to conserved. And opposite. Equal in magnitude, opposite in sign. So here's what the equation would look like that you fill into the box for recoil. Momentum of object 1 is equal to the momentum of object 2, except for it just has the opposite sign with it. So yes, momentum is conserved, equal in magnitude. That's the fact that allows it to be conserved. Once you finish copying that equation, then you can flip your page and let's look at the practice problem for your recoil scenario. The last example on the class practice says, a 2 kilogram rocket zooms upward at 5 meters per second. It's propelled by 1 kilogram of water shooting downward. How fast does the water shoot out downward to propel this rocket? So we have a 2 kilogram rocket going 5 meters per second, but we only have 1 kilogram of water that is powering. Yeah, that was weird. We only have half as much water to power the motion of that rocket. So if it's going to be powered by 1 kilogram of water, that water has to shoot out of the back end going pretty doggone fast in order to get a rocket that's twice its size to travel 5 meters per second. Again, the water used is half as massive, so you can kind of figure out what kind of velocity it's going to move at. If the concept escapes you, let's apply the math. So there's your recoil. A way to identify that this is a recoil scenario, other than the fact that we're on that slide, if this were mixed into a problem set, once you see the upward and the downward, those are opposites. that in itself keys you into the fact that we have recoil. Another example of this is like a lot of times we like to talk about cannons being fired. The cannon the cannonball goes forward, but the cannon itself is going to recoil and launch backward. We've all seen an example of that about the opposite motion. Okay, so when you plug in the numbers, here's what we'll go with. In the beginning, the rocket we can call object 1, and the water we can call object 2. So we'll plug that in over on the right-hand side. Another indicator that the water is object 2 is looking at the scenario, the water's shooting downwards, so it has to be the one that's negative because it's down. Think of your sign conventions that we learned at the beginning of the year. Down is negative, up is positive. If you were talking about the left-right type of scenario that you're going to encounter, like with a cannon recoiling, an object that travels to the right, positive, an object that travels to the left is negative. Okay, so here's the rocket. It's positive because it's going upward. So we'll put the 2 and the 5 here on the left-hand side. There it is. The negative is part of the equation, so let's fill in the mass of the water, since it's the negative direction downward, and then the velocity is our unknown to figure out. When we multiply together on the left-hand side, you get 10, and the 1 times the v gives you negative v2. Well, we don't want the answer to negative v2, so how can we change it into saying that we want positive v2? We'll switch the signs. If negative v2 is equal to 10, then positive v2 is equal to negative 10. Okay, we're going to have a question and answer session, so we'll open it up for questions if any of this has confused you. But in the end, it all checks out. The momentum of the rocket is equal to the momentum of the exhaust. That's the water. They're equal in magnitude, so we can say that this is true. Opposite signs, but equal in magnitude. That is going to conclude your notes for today. Enjoy.